My role, just to introduce myself, is I'm kind of jack of all trades or Swiss knife of control because I'm teaching, I'm having students, I'm doing education programs in corporates. I'm working with government. I wrote a book that you can download. Podcasts. So I do many things. So it's usually you say you're a consultant and you do that. Yeah, I hate that word. I know that when you're a consultant, you're like kind of divine. But that's what I do. And also, I'm the co-founder, one of the co-founders of the QEI, Quantum Energy Initiative. We can talk about it in my presentation. So here we go. Let's start with what I call the promise of quantum computing. It's been talked about in various presentations today and yesterday. It's still a good one because most of the time it's been explained that quantum computing is going to improve the speed of computing for scientific purpose, for example. It is supposed to turn a so-called exponential problem into a problem that's not exponential in time. So we have the famous ESP problem, the triangle self-solving problem, that's known to be exponential. So we've got a lot of chemical simulation problems that are supposed to be exponential, and it should be turned into something that's not exponential. That's the promise, I would say. And most of the time we say, okay, but there's Moore's law. You know, that doubles the power of classical computers, particularly with supercomputing systems. It happens that Moore's law is just doubling every, few years or so the power. People believe that it stopped, but it didn't stop really. And I just recently wrote a paper on arXiv that's called "Is there a Moore's law in quantum computing?" Moore's law has not stopped in classical computing. What has stopped is the improvement of the density, the number of transistors in classical chipsets still is improving. If you look at the latest NVIDIA chipset, it's what 100 billion transistors. It's much better than what we had just 2 years before. But the chipset is bigger and not necessarily highly integrated. And you have supercomputers like the Frontier Aurora that's based in Oak Ridge in Tennessee, which is much bigger than the one that was created in the same place 5 years ago, the IBM Summit. So there are some progress going on, but it's only doubling the power every 2 years. And an exponential problem doubles the requirement for computing every other 2 variables that you or 1 variable that you add. So the speed at which the requirement is increasing with an exponential problem is much faster than the speed at which Moore's law is being applied. So the promise is to turn, let's say, an exponential problem into something that's not exponential. But then the divide is in the detail. So what is the transformation? So is it transforming something that is exponential into a polynomial problem? Or is it linear? Is it logarithmic? It happens that more or less half of the known algorithms in quantum computing are not providing an exponential improvement. The famous Grover algorithm that was discussed by Philippe yesterday is only improving by quadratic, it's square n. So it's not as good as an exponential improvement. There are still a lot of algorithms that belong to that class. So why do we need that? So it's supposed to solve intractable problems. So those problems that grow exponentially. And there are various ways to sort out the use cases. One way is to look at all the classes of the optimization problems. And we could say that more or less all of the problems that the quantum computer could solve are kinds of optimization problems. So the most famous ones are the optimization problem that you manage in operational result. So the TSP problem. There was a case study yesterday on the fab shop optimization. You have various optimization in transportation, in logistics. So that's one thing. It's more or less binary optimizations. Then we have physical simulation. So physical simulation, most of the time, it's about finding the ground state, the energy of the complex system, so it could be a molecule or chemical interaction between different molecules. So it's about finding a minimum. But sometimes it's even more complicated. Sometimes you want to find a 3D structure of something. It's not just a minimum, it can be more complicated. Then you have, I would say, engineering as a whole. So there you can have various kinds of linear or non-linear equations that you want to solve to do something in the aerospace business that may be complicated today. And in the end, you've got the whole bunch of machine learning techniques that may be improved thanks to quantum computing to some extent. And then the last one I hate to mention, which is show algorithms, factoring integer to break the security of the internet. I don't view that as a very positive use case for quantum computing. It's something that may happen someday, but it's not very positive. There's no positive use case of that. So this can change society to some extent, but breaking the internet, I don't know what kind of business it is, pirates, NSA, whoever, it's not a positive business case. So that's why I hate to put that in. So then who could use that potentially, because it doesn't exist yet. So potentially you have, I would say, two classes of potential users for those systems. The first class is research itself. So quantum computing can help researchers find new things. So find new drugs, find new chemical processes, the famous so-called fertilizer process using the Haber-Bosch process invented in Germany more than 1 century ago could be improved to some extent if we're able to simulate how nature works in that sense. Inventing new batteries. So those are all the big space of research. And it's very important from a business standpoint, because here you've got a rather small number of researchers that could improve science. And then, if it works, the implementation of those inventions are implemented in classical ways. So, for example, if you improve the production of fertilizers, the production itself is not quantum. It's based on chemical industry, whatever, a new process. It's the same. Let's say, for example, you improve the layout of the superconducting semiconductor circuit. It's about optimization. There's a lot of theories behind that. So if you improve that, but then you manufacture the chipset, it comes into your laptop or your smartphone. It's not quantum anymore, at least from the second generation of quantum technology definition. And there are some researchers, I like that because it's kind of weird. At CERN in Geneva, they are starting to try to use quantum algorithms to just sort out the boson Higgs, the Higgs boson, out of the experiments using machine learning. Others are trying to detect dark matter using special sensors in astrophysics. So this is physics and research outside of the commercial realm, I would say. The 6 top things here have applications in industry. But then you have what we call operations. Operations is how do you improve the day-to-day operations of your businesses. So it can be a bank or any financial institution that wants to improve the portfolio optimization and at risk for insurance. These are optimization problems that could use, to some extent, quantum computing. All the business of transportation, I know lasers here. So transportation and logistics and delivery, that's the kind of thing that people are doing to improve thanks to optimization algorithms running on quantum computers. And I have always to say that's potential. It doesn't exist yet. That's the dream. We know that for most of the cases presented here, the hardware requirements are way beyond imagination with what we have today. All the current quantum computers are way can't do anything that's in that list as far as I know. But there are new potential use cases that people talk about in marketing, in communication, in media. But those people, first, they don't have a lot of money, particularly in media. So we don't talk about it now. But maybe in the future, when quantum computers will become mainstream, maybe some use cases in various businesses will happen. So energy utilities, there are both ways, because energy, you can improve energy, the research about producing or transforming energy or storing energy, like with batteries. And on the other hand, on the operational side of things, you can improve the distribution of energy, which is more an operational thing for a day, for example. So these are the kind of use cases. Now, I stop talking about the business issues. We're going to talk about science. So Simon presented qubits this morning. I will compliment his presentation. So I'm going to use the block sphere. And the reason why there's this Euclidean presentation from Simon and this block sphere presentation. The block sphere presentation is weird because, the 0 is the side, it's north power. The 1 is south pole. And they are like this, but they are orthogonal mathematically. So it's very logical to be like this. So there's a historical reason why it's the case. But the historical reason comes from physics. Why is that? It's because the block sphere was inspired by 2 other spheres One is the Poincare sphere that was used to show the polarization of photons. And you have circular and linear polarization using this kind of field. And there is another sphere that's more or less the same about the electron speed. So spin up, spin down. So those two historical reasons explain why it's that. But there is another one that I find very useful to explain. One of the reasons is all the qubits we are managing, whether they are photons, superconducting qubits, atoms for which you control the energy level or even the spin for an electron, all these qubits behave as waves. And those waves, they have an amplitude and a phase. So, and we are toying in algorithms with the phase and amplitude of those objects. And it shows up like this. So the phase is how you turn around on the equator, if you are superposed perfect position between 0 and 1. And the amplitude is, are you in the northern hemisphere or the southern hemisphere? So it shows up very clearly where you are, and then you can explain how you toy with that, and we show you a couple of examples. So that's the basics. A qubit, by definition, is a two-level quantum system that you can control from a physical standpoint. You can control two energy levels for an atom, 3 not 4. Otherwise, it will become a qubit or a qubit. It's a variation of qubits. You can control the transition between those two levels. You can superpose those two levels. You can manage also entanglement between various objects. So the basis is two-level system that you can control some way. You can reset it, you can read it, you can manage the superposition. That's the first requirement. The second thing that's very weird, and Simon presented that, it's that when you have several qubits together, the composition, the composite system assembling those qubits, it's creating kind of space of information that scales as 2 power n. So we have 2 power n complex numbers describing the system. And if you want to have a very simple mathematical view of that, it's just that you're managing 2 power n complex amplitude, complex number, which means 2 power n plus 1 real numbers or floating numbers, if you want to talk in a computing parlance. And that's the space you're managing. And then you have those 2 qubit gates, or several qubit gates that can connect the qubits together. And the entanglement creates the links. And those links are one of the sources of the power of parallelization and in quantum computing. But there are many details that explain that that is not enough to explain where and when you could have an exponential acceleration. It's not enough to have 2 qubit gates. It's not enough to have an entanglement. It's not enough to have those 2 power n amplitudes to get an exponential acceleration. There are other conditions. Mostly, you need to have so-called maximally entangled states. So you need to have a lot of entanglement. All the qubits have to be entangled. Otherwise, you won't benefit from the scale of this large computing space. And the other thing is you need to have special gates to get this acceleration. Because if you have only so-called Clifford gates, so the gates that do only half or 1/4 or one half turn in the block sphere, you won't have an exponential acceleration. You need to have special gates. So Ry theta and Rz theta. These are the gates that can implement an arbitrary rotation around the 3 axes. And it happens that I don't know if it's going to show up. I lost. There's something in Zoom that's preventing me to move a bit. Here we are. So it happens that if you are in the so-called fault-tolerant regime, so very large-scale quantum computers with logical qubits, you will use more or less the VSMT gate to do the rotation. And if you are in the so-called near-term systems, no intermediate scale quantum computers, you will use the R gates that do arbitrary rotations. That's a big difference when you program the system. So then, if you look at the mathematical standpoint, another way to present the way you manage the 2 qubit gate. So let's say you have 2 qubits. The 2 qubits can be described with the amplitudes. There are 4 amplitudes that describe the 2 qubits. So alpha 00 to alpha 01. And if you apply, for example, a swap gate, you will swap the 2 qubits and it will swap the coefficient. So the 2 in the middle will be swapped. if you implement another kind of gate called control unitary, so control any transformation of the secondary qubit based on the control qubit that's on the top, you can apply those various coefficients, and that's just a matrix multiplied by a vector. So that's a kind of mathematical view of that. There are many different ways to understand how quantum computing works. You can use the electronics analogy, because most of the algorithms are, particularly in the fault tolerance space, they are based on phase estimate, phase amplification, Fourier transform, reverse Fourier transform. We manage concepts that are very close to analog electronics. Then you can have the mathematical standpoint. Then you have the physics standpoint using the bracket notation from Dirac. There are many different ways to look at the way you program the system. And then you have the special case of analog computing, which you can find in the now we have measurements. So you've got this amplitude. So you've got a 2 power n complex system. You apply to those qubits many gates. So there's the program with a time in x and the number of qubits in v on this kind of schematic. That's just another. Yes, it's another for 6 qubits. Very simple. It's just making additions. And in the end, you measure, and you get a result that's a 0 or 1. So what I like to say is, during computation, you've got an access to a very wealthy data environment. At the beginning, you just get zeros, and in the end, you just get zeros and ones. So it's wealthy inside, it's poor outside. And the wealth of computing comes from all the gates you apply, and the gates are being used either to feed the algorithm with some input data, and you need gates to input data, then you do some computation, then you read out those very poor bits in the end. So the question is, how do you get some wealthy data outside of that? So there are many ways to do that, but most of the time what you do is you implement your algorithm, you run it several times, and you do an average of the output bits. And there are many ways to do that. So if you use a typical run on an existing computer in the cloud today from IBM or anybody else, you really run your code about 2,000 times, 4,000 times, 8,000 times. You do an average, there's noise, and you see where it lands, and that's your result. If you were to do that with a so-called variational quantum eigensolver algorithm that's supposed to help you find the ground state of a complicated chemical system, I said enormous, so it can be billions of times of execution. It can be very long. It can last several years, potentially. So it can be very long. There is something that's wrong about when we talk about quantum computers. You may have read the Time magazine cover page back in January. It said that the quantum computer was computing instantaneously instead of many years for a classical computer. That's not true. It's not true. It happens that quantum computing is very slow. It's weird. It's supposed to be fast, but it's slow. There's a contradiction here. The contradiction comes from the fact that a quantum computer is supposed to turn a very complicated problem for a classical system into a less complicated problem. But it means that the complicated problem that is supposed to be hard to solve on the classical system may last maybe sometimes billions of years on the classical computer, and then it turns into something that's faster. But faster can be still several months. For example, the potential application of Shor algorithm to break an RSA of 2048 bit lasts 8 hours. It's not instantaneous. So if you want to break the Bitcoin with that, it's too long, 8 hours. So 8 hours is quite fast. There are some algorithms on chemical simulation that last tens of years. So instead of billions of years. So it's not instantaneous. The other thing is, most of the time we think that because a quantum register with n qubits as a kind of data space of 2 power n complex number, that explains the exponential speed up. It's not true. Not entirely true. You need that to get some acceleration, but it's not enough. The time advantage comes from the length of your algorithm. It comes from the number of gates you have in your algorithm. So if the number of gates is increasing as fast as the number of classical instructions in a classical algorithm, it won't be fine. Particularly given one gate in a typical quantum computer is very slow. The fastest systems I know have gates that last about between 20 nanoseconds and 400 nanoseconds in superconducting qubits, which are rather fast. With trapped ions, it's 1,000 times slower. So trapped ions, it's not in nanoseconds, it's microseconds. The scale, and it's very slow. If you compare that to a 3 gigahertz system, it's a couple of nanoseconds for one instruction, and it's parallelized. So the speed of the gates is a very important factor for the speed up of the quantum computer. You need to look at the constant, you need to look at all the variables of the execution time of the system. That's one thing. But the other thing is there are so many ways to assemble an algorithm that you can have sometimes a polynomial, you turn something like exponential into polynomial scale. Sometimes it's much better. It depends on the algorithms. And it depends about those factors I mentioned, the type of gates you use, the size of the entanglement you have in your whole system. If you have, let's say, instead of two parallel systems, if you divide your n into 3 parts, and you have, let's say, n divided by 3 qubits that are entirely entangled, then you have another set of 1/3 of the qubits entangled, and then another set of 1/3 of the qubits are entangled. This is going to be way less powerful than 2 power n entangled qubits. Because the power of entanglement is the power that brings the power of the qubit. And so it's not fast. The number of gates can scale polynomially or semi-polynomially with the number of qubits. And if you have so-called non-shallow algorithms, so kind of deep algorithms, you will have to implement error correction, which will add its own overhead, and then you will have to compute how long it takes to compute. So it's not that simple, I would say. It's more complicated than we used to say when we talk to general algorithms. And exactly like in classical computing, you have a trade-off between space and time. So for example, if you have no qubits, quality qubits available, you will be in a position to have a faster algorithm. Otherwise, it's the other way around. If you have not enough qubits, maybe your algorithm is going to be too long or longer. And there's another factor that can be boiled in here is there are some futuristic architectures where you can have quantum memory next door to the computing qubits, and they will exchange data. And the quantum memory is a kind of slow, but you can feed it with data. And when it's fed, you transfer the data to computing qubits, and then you compute fast. And the combination of those two systems can bring also its own trade-offs. And there were some works done by Nicolas Amboire and Olivier Ezratty at CEA at UNIT. It's a joint CNRS-CEA lab in Saclay. And they did show that with a fewer number of computing qubits and a lot of qubits dedicated to memory, you could have interesting solutions that may be easier to develop. So what is changing? If you are a developer, particularly if you are a mathematician or developer in the operational research world, but one thing is when you design your first algorithm, you toy with the graphical tool sets like Quark or tools from IBM and others. So it's a way to understand how it works. There are very nice data inspectors available in those tools. I love Quark for that reason. You can put your density matrix, your vector space. You can look at the data while you are training your algorithm. But then when you become serious and when you have a large algorithm, you play with Python. One reason is if you have a large algorithm with many qubits, you will have kind of redundant structures, kind of graphs, and it's going to be easier to design them with Python code with some repetition and loops instead of designing them with hands and designing the graphic design that you have on that. The other thing is you need to do math. So probably it's not trying for you, but when you take into account the 95% of the PhD developers who design the websites, it's going to be a big challenge for them if they want to do some quantum computing. You need to do math. I don't know any other option. There's no other option. The second thing that's interesting is you won't design your software as usual. It's not like in JavaScript. You can do pause. You make a breakpoint. You make a pause. You look at the variables, and then you say, I'm going to change variable, change some instructions, then I go forward in the code. You could do that theoretically in quantum computing, but what you have to do if you do that is you will have to get to the next line of code, let's say. You will have to execute from the beginning everything a couple thousand times, maybe a couple of hours. to get just to the next slide. So what people do usually, they use emulators, so classical emulators of your own code, to look at the data while it's computing on the classical system. And when it works, you can scale that to a larger number of qubits that wouldn't be accessible to an emulator. And then you have to try to guess, or find a way to prove that the result out of your system is verified. There are ways to do that. And the last one is, I love that from the perspective of classical computing engineering, is you can't copy data independently. Because of the no-cloning theorem from quantum physics, you can't copy data. So you can transfer the data. There are teleportation algorithms that can help transfer data from one qubit to the other, or one set of qubits to other qubits, but you can't copy independently the data. Or I think you can copy the exact vector state from one set of qubits to another set of qubits. It's just a constraint you have to know. So you play with the system where all the rules that you have in classical engineering are different in the quantum world. Now, another question that may arise when you discover that law is, what are the concepts behind coding? If you look at classical computing, you have so-called different level of abstraction. So maybe some of you have learned assembly language in the past to develop drivers or develop embedded systems. Maybe some of you have developed in C or C++. And most of people now, when they do machine learning, they develop in Python with frameworks like TensorFlow or PyTorch. And sometimes people talk about the no-code system. There's even no code, just parameters, kind of very high-level software. If you look at quantum, where you have different layers of abstraction, you can code with TCP, for example, as a top layer. You may use an application-specific framework for chemical engineering, optimization, whatever. But when you use the compiler that's turning the code into some code that can be read out of the machine, it's always the same level of abstraction. It's always gates. It may be different gates because the gates that are available at the hardware level may be different than the one you use as a developer, but it's always the same gate-based paradigm. And it happens that today, if you compare the kinds of data you are managing in those two different, I would say, scenarios, in classical computing, the higher you are, the higher data abstractions you have. You can manage arrays, tables, objects, or whatever you call it. But when you are in the quantum ring, you manage more qubits. Hopefully, there are some kind of objects that can show up now. You have collections of qubits. You can have, let's say, the output of some algorithm like QFT or HHL for those who know. So there are some kinds of algorithms that output a specific set of data, but it's still the same abstraction. It's qubits from this layer to that layer. The only difference is here, electronics, because at the end, when you've got the basic gates that are the gates that are implementable on your system, they are turned into electronics, I would say, instructions that drive something I will show later, which are all the electronic systems that drive your qubits. That you don't care. If you're a developer, you don't care about it, unless you are developing that layer. But usually people don't care about how you drive the detail, the gate on your system. So I like to say it would be easier if it was not more complicated, but it is more complicated because you have different paradigms. Yesterday, you had two presentations on D-Wave, if I remember well. There was one presentation from the team from Pascal. So these belong to different paradigms of computing. So the typical paradigm that we use is gate-based, but you have the quantum engineering paradigm, which is more or less a kind of complicated neural network that you manage with qubits. And then you have the quantum simulator or analog quantum computers, which is another different paradigm. People used to say that the last one is more flexible than the second, because you have more flexibility in the way you design the graph and the connectivity between your qubits, when in quantum annealers you have a static layout of the qubits and the connection between those qubits. It's more flexible in Pascal, for example, or the computer in the US named QERA from Harvard. But there are many different ways to control the interaction between the qubits in those so-called analog systems. And you have a bit more flexibility, probably potentially more power. But there is an open question. One of the open questions that we have is how those different paradigms can scale. And we don't know yet. We don't know, for example, how far we're going to go with Wave. We had a discussion yesterday about how many qubits do they have and how do we scale? We don't know either how do we scale with neutral atoms. Because it's still unknown how many entangled states we can control with how many atoms can be positioned in space and control. Can we have long distance entanglement between all these atoms? Those are physics questions that are still unanswered, and they require both work in theory and in experiments to get the answer. Now, algorithms. This is just, it's kind of a joke because you can't read that. Let me do some voiceover that slide. I hear a lot from various people that there are not many quantum algorithms. I hear that a lot. Let's say there are only 5 algorithms. Maybe we have some classes of algorithms, but what I find in the literature is there are many algorithms. There are many algorithms that correspond to different paradigms that I described just before. There are also algorithms that are designed for long-term quantum computers, others for short-term quantum computers. There are a lot of variations. And I would say that the quantum ecosystem is quite healthy. I mean, I see every day, every other day, there are new papers on archive, new algorithms, new variations of algorithms, new optimizations, because many researchers in that space want to optimize those systems. And one important thing is all those people designing algorithms, they have to care about the resources it's going to use. They have to care about on what kind of system it can work. So some algorithm designers are working on very theoretical work, and others are trying to care about the resources it can exploit, because they want to make sure that it can use someday. And there are some required interaction between the people designing the algorithms on one end, and the people who are designing the hardware systems that are going to run those algorithms. So there's a lot of collaboration that's needed. So why do we have those layers? The reason I try to design that side is because I want to understand, okay, quantum two-way transform is a very important algorithm, but it's being used in HHL, that's used for linear algebra. But then you have machine learning that's based on HHL. So you have different layers of algorithms that are using the lower layer. And so how is it constructed? It's kind of bizarre, strange. That's one question I had. The second question I had is, how do you sort out those algorithms that are made for fault-tolerant quantum systems that are going to use logical qubits in the long term, with billions and millions of qubits? And what are the classes of algorithms that can be used in the short term, in the so-called NISQ system? The other question I had is, how do you compare the algorithms that are designed for analog systems, so D-Wave and Pascal, to those algorithms that are designed for gate-based systems? How do you compare them? And is there a real difference between the algorithms that target analog systems and gate-based systems? When you look at the, I would say, the business need or the application need, it happens that many of the needs that are supposed to be covered by quantum systems can be implemented either in analog way and gate-based way. That's why I've got this kind of green and red or blue color at the top layer. Many quantum machine learning systems, many optimization problems, many quantum simulation problems have a kind of implementation possible on analog systems and implementation on gate-based systems. The scale is different because we don't know how the system will scale, but there are variations. So let me describe, for example, one example. If you want to do an optimization, so all those Maxcut, TSP, SAT problems, you can implement them in a classical gate-based way through, say, the blue algorithms that go through a gate-based system. And you can implement them also through a QBO optimization algorithm that runs on an analog system, either on Pascal or D-Wave. That's an example. The blue here corresponds to what you could theoretically run, at least for those two parts here, on a near-term quantum system that is gate-based. So let's say IBM or future IBM systems. It can go through variational algorithm for, let's say, ground state combination. QAOA, that's an optimization algorithm that can use those systems also on gate-based systems. But there are other ways through the so-called QBO that runs on the other system. It's a bit complicated, but it's interesting to know the various paths we have with all these different algorithms to have a kind of helicopter view of what is available. And I designed that chart, but I didn't find it anywhere else. I think I was inspired by some paper, some review paper that was published about 4 years ago, but I did update it on the fly because I was learning myself. And we would say, what why do you have this thing here? Because cubic teleportation can be used in quantum communication. But you know, there are algorithms that are based on teleporting a gate. And it can be used in classical gate-based computing. So those algorithms that are mostly designed for, let's say, quantum communication, QKD kind of stuff, it can be used in classical algorithms, gate-based at least from there over there. So that's the thing. Now, how would you rate a quantum algorithm? How would you rate a system? If you were a user, the first thing I would say, it's obvious, but you have to remind that, is that it solves some useful problem, whether it's for research or for a company operation, it has to be useful. Why is that important? Because most of the quantum supremacy experiments, particularly the one from Google, is not solving any problem because it doesn't get any data as input. There's no data. It's just randomized benchmarking system that creates a set of random gates that are hard to simulate digitally, but it doesn't get any input data. The same for Gaussian boson sampling that is being done by Chinese and Xanadu in Canada. Mostly those systems are using random gates, a random system that's not creating some useful data. So you have to have data as input and data as the output to make something that's useful. Otherwise, it's just a random number generator. The second is it has to bring some benefit compared to the best-in-class system that could run on a classical system. So what is the kind of benefit you can expect? The classical one that was in my first slide is exponential or whatever acceleration. It could be a quality improvement in the result. Let's say you have a quantum machine learning system. It could be better to at least to extend, less training data, maybe. Maybe a better prediction, a better classification rate, error rate that you could have in machine learning. It could be also various other quantitative results, not quantitative, not faster, but better. The last one could be maybe an energetic advantage. It happens that most of the known quantum algorithms, those I know, the system you can expect to have in the next 15 years, they don't use a lot of data. One of the reasons is the gates are slow. It takes a lot of time to put data in the system. So one wrong idea that's conveyed by some analysts or consultants or whoever is, okay, quantum computers is for big data. I don't know who agrees with that, but I've never seen any real big data solution entirely implemented in quantum. What you could do is you could implement some kind of machine learning system with a classical part that does the shitty work of managing the big data, but it will turn a large set of data into a smaller set of data that then feeds a quantum system. That could work potentially. But a full big data system that ingests billions of records of whatever data you have, that's not good for quantum systems. Another one is, can you, based on your business needs or your research needs, can you estimate the hardware resources that you will need? I don't know if it works well in classical computing, but still you know what to run in an NVIDIA GPU or DGX rack of servers. You know what can run on a Jean Zay or Joliot Curie supercomputer in France. You have some idea of what you could run potentially. But still, since the science of quantum computing is quite new, we lack the knowledge to do that on a regular basis. So we have to design new tools, new resource estimate tools that can help you expect or define what you can expect to run on each kind of machine. If you do that today, you will have disappointments because you will find that there are not machines available to do what you want to do. But still, it can help also create the roadmaps for all the hardware vendors, for example. Because you need to know what's going to be needed to solve a given problem to design machines. So some synchronization needed there. The last one is how do you verify that your software runs well? How do you verify it? Let's say you're in the cloud. You send some data, some quantum algorithm from the cloud on the system, and it returns an answer. How do you verify that the answer corresponds to your input data? It's a theoretical need for all computing, I mean, classical and quantum. But since you don't control the same way what happens during computing, you can't inspect the data throughout the whole computing process. You will have to design new tools, and there are people working on that. How do you verify that what comes out is what comes in? So correspond to what came in the system. some hardware now. I don't have a lot of time for that. You know, there are many kinds of qubits. Usually we segment that in two categories, stationary qubits and flying qubits. A stationary qubit is more or less a qubit that doesn't move. So it's somewhere in a circuit, that's what we have. So it can be a superconducting circuit, it can be an ion or a neutral atom that's stabilized somewhere in space, in 2D or 3D. It can be also a spin of an electron spin that's stabilized somewhere. But it happens that any atom or any spin or any electron that's trapped somewhere, it's always moving. The Heisenberg principle explains that it's always moving. It's still controlled in a narrow location, and you can control them with some microwaves or some photons, and you can stabilize them somewhere. And then you have photons or even tiny electrons that can move around in circuits. And the way you design the computing architecture with those tiny qubits is a bit different. Because since it's moving, it starts from the source, it goes through different circuits, mostly semiconducting circuits, and then you detect the electron or the photon at the exit, which is entirely different from a system that doesn't move, where the system is at the same location when you initialize it, and you read the state of the qubit at the end of your process. Another way to look at this is most of the systems, besides only one, which is neutral atoms in the type of Pascal, all the other systems are based on some circuits. So trapped ions, superconducting qubits, electron spinning, photons, they all use a semiconducting circuit, a 2D circuit. It's manufactured using different techniques. Some of them are inspired by the CMOS production technique, others are kind of variations of this technique. Superconducting qubits, for example, are manufactured with a very different process than CMOS, using the fab that Neil described just earlier, that is being built at STEC in SATEC or SEVA. But those are always semiconducting cells. One question you should have or you may have is how do you control the qubits? So how do you change the state of a qubit? How do you connect them? How do you manage entanglement between this? You always, nearly always, use a photon. You send a photon on one or several qubits to control them. But the photon is very different from qubit to qubit. If you're using a superconducting qubit or electron spin qubit, you use microwave photons. So it's photons in the 5-6 gigahertz regime, up to 20-something gigahertz regime. When for trapped ions, for cold atoms, and for photons themselves, you will use photons in a more the visible infrared space. So it's much higher frequencies. It's different settings. You have lasers, you have photons. It's very different things. But you always use photons. And one big question that I had when I started in that place, how do you manage entanglement? Most of the time, you send kind of entangled photons to two objects, and it creates some entanglement between those two things. And these are variations of this. So you have to send some wave, some electromagnetic wave to the qubit to create that entanglement and the change of position in the log sphere for each of the qubits. One weird thing is we don't yet have a fully functional quantum computer available right now, but we have about, I don't know, the number of items on the top. These are research labs below that line, and these are industry vendors. So including ones, IBM, Google, and startups like the French ones, Candela, Pascal, and so on. So what is interesting here is you've got more than 50 companies designing a quantum computer. About, I would say, 15 of them have already put their machines in the cloud, in Amazon, Microsoft, Google Cloud, IBM has its own cloud. We have OVH in France. But none of them has a functional system that brings that exponential advantage that we discussed. Not yet. So these are more private research companies having put in the cloud prototype systems that are very useful to learn, to look at what happens with qubits, to look at the impact of noise in qubits or existing algorithms. It can help us understand how to scale some way, but these are still mostly prototypes. The closer of these companies become production grade use cases are mostly the analog systems. So those who are in the polynomial category over there, particularly Pascal and URA. Then you've got G-Wave, small computers, those ones are minor. So there are three companies who are not far from doing something useful, and all the rest, we see that there's a lot of challenges remaining there. So how does it look like? You may wonder what's inside that box. So it's figuratively and usually a black box, and we're going to open the black box. So let's take the black box from idea. So it's a bit designed here. So what is that cylinder? So that cylinder is having about 5 layers of cylinders inside. So we've got a chipset at the bottom at 50 millikelvin. The top is at 450 Kelvin here. There's a lot of cables over there. And this is put in vacuum. It's isolated magnetically. And there's some cooling system. So there's a significant cooling system over there using helium 3 and 4. It costs more than €1 million just for the cooling system. It comes mainly from Blue from Finland, in the region in that sense. Everything is in that system. And then you have an external compressor because the system is cooling here, but it has to be cooled with water. So you've got another compressor outside. Just remind you that it's a gas factory, or like we say in French. Then you have electronics, and you have more racks for electronics than for the qubits. So if you take a system from Google or from IBM, the space taken by the control electronics that control the qubit is bigger than all that thing here. And then you've got a classical computer, always, a couple of ones. There's a one for compiling, a one for executing the code, a one for connecting the system to the cloud, there's a networking switch. All that is a kind of, I would say, computing rack, electronic racks. And so a quantum computer is always a mix of 4 things. Classical computing, classical electronics, some quantum stuff, at whatever temperature it is, and then some cooling system, depending on the type of qubit that you have here. So that's what we have. Now, look at the chipset that's here. The chipset is open circuit. If you look at the mapping of the circuit, it looks like some electronics. It's put in a matrix that the Google Sycamore system will fit in. Then it's put in a kind of packaging that's regular, the kind of packaging you have in the classical system, but it's put in a specific packaging, sometimes vacuums. So you see that it looks like a military system. So it's there's a lot of metal. And there are weird connectors over there. It's coaxial connectors. These are connected to a lot of cables that are inside the fridge over there. And it's connected to a lot of electronics. And you see a lot of wires outside. That's a superconducting existing quantum computer. That's the one from Google. That's on my book and the slides. It's easy to get. So, but if you take a photon qubit system like the ones from Candela, it's a bit simpler. You still have a classical computer. You still have electronics, but we control a laser, a unique photon generator that feeds the kind of photonic circuit. This is not cooled, and then there are photon detectors, and then you export the results. But the cooling is different. You have to cool the source of the qubit, the source of photons, and you cool the detectors. But you cool them at a higher temperature, like between 3 and 10 Kelvin, doing the simpler cooling system. The size of the cooling system in Candela is just the bottom of the rack over there. So it's much smaller. So potentially, when that works, a system with photon qubit can be a bit smaller. But so at this point in time, it doesn't control a lot of qubits, a lot of photons. But it may scale differently from the superconducting qubits. Big question is, when is that going to show up? You know what's the right answer? When will we have a quantum computer bringing an exponential acceleration, solving all the problems I described? What is the right answer? Huh? You don't know. I don't know. But you know what you do when you don't know? You elaborate a little bit. You try to find a way to explain what's going to be the story.
It's always the next 5 years.
Yeah, well, next 15 years.
No, it's always the next 5 years. Next year is again.
No, well, it's not to whom you talk about it. Usually people say 15 years because 15 is far enough to be controllable, but it's still in your lifetime. Like, if you're 60 like me, it's your lifetime. If you say 50 years, it's too late. I want to see that. So 15 years is kind of in between. So one way to describe the roadmap to those quantum systems is to say we have more or less prototypes. we are entering a so-called noisy system that could be useful. And later, probably in 2 years or not, we will have fault-tolerant systems with special characteristics. Well, the naive part, we have this in 50 years. An optimistic part to say we're going to have continuous progress, like always with innovation, like in the last 75 years of physical computing. Each and every year, we're going to have more qubits, more quality of the qubits, more algorithms, more use cases. And we'll see what happens. Another way to look at this is saying that, well, the pessimistic part at some point will reach some threshold that shows that it's impossible to beat large entangled space systems. We don't know. Another way to look at this is we are in the small-scale experiment right now. Maybe in the next 5 to 10 years, we have some kind of early small-scale advantage compared to classical systems. Maybe it can be a qualitative advantage, not just a speed-up advantage. And maybe in 15 years, we can have more generic advantage, large-scale quantum computers, but we don't know exactly. But that's a potential case. What we don't know is what will happen with innovation. We don't know if topological qubits for Microsoft will work. We don't know if photonic qubits will work with Quantum, Candela, and others. We don't know if any other kind of qubit will show up that's maybe showing better quality, less noise, and so on. So there are so many different options that we saw in the previous slide that we are facing a kind of Cambrian explosion of technologies. We still have to let people invent what they can invent in their own space, even though sometimes they are in very small niche. I was in Las Vegas a month ago at the APS meeting. It's the largest physics meeting with 13,000 physicists. And I met a company called HeroQ. Nobody knows them. They're just based in the US. And what they do is they are tracking electron spin on top of a helium superfree liquid. And you say, why not? But who knows if it works or not? So I took some detail. You don't know. You have to be open to. Now I have to talk, but I'm going to have to be very fast to NIST. So the NIST is what we should use in the next 10 years. So we have to be serious about that, because if you want to use the NIST, we have to know the constraints, we have to know what kind of algorithms we're going to run those systems. We have to look at the resource constraints of those systems before we have a fault-tolerant system with billions of qubits and a logical qubits and so on. So NIST was defined exactly 5 years ago by John Presley. I had a chance to meet him in Vegas, discussed with him about that. And he said that maybe we're going to have some intermediate solution with a noisy qubit that still can be useful, and we'll see. What kind of algorithms can you run on this system? Most of the currently designed algorithms for those systems are so-called variational algorithms. Those are systems where you combine a classical system that prepares some ansatz, or some kind of computing that's being run on the quantum computer, and they are circling around, so trying to optimize some cost function. And it's usually sorted in 3 categories, so or 4. So variational algorithms, variations of eigensolver that is for physics simulation. You have QIOL, that's mostly interesting for you in operational research, so it's made for binary optimizations and other kinds of optimizations. Then you've got variational quantum linear solvers, mostly for to solve linear equations. And in the end, you've got quantum machine learning with both use cases in many dimensions. But the ones that you have in orange over there, search algorithms, QFT-based algorithms, those are outside the scope of NIST. You can't run that on each system, so it's only for fault-tolerant system in the long term. So just to have an idea of what would be required at the hardware level and the time scale level, I will show you how it's working. It's just a personal discovery that's quite easy. So a classical variational algorithm running on the NIST system is using rotational gates over there. So it's just rotation in the box here of arbitrary angles. Then you've got some CNOT entangled gates, and this block of code is repeated a couple of times. One L. Where is the L? The L is over there. So you have blocks of this, and the number of repetition depends on the algorithm and the kind of things you want to do. So the question is how many hairs you have. it depends on the solution. Then you measure the results in using so-called polystring. So what you do is you turn your block sphere by half turns to change the basis of measurement. You do some measurement, and the question is how many of these situations you have to create. And for each of the situations, we have to do computing a couple of times for each of the basic measurements. The scale of that is order of magnitude, number of qubits power n, n can be 1 for QAOA, so optimization problem. But if you do some chemical simulation, it's n equals 4 or 3. So it scales very fast, even though it's polynomial. Then, how many times you do an execution of all these circuits for each of the polystrings here, just to get a good precision of computing. You do that in a scale that's 1 divided by the precision of the error rate power 2. So let's say you want to have a good precision for a chemical simulation. You will have to run your algorithm 1 million times for each of the polystrings. Then you have the classical computing. So you have error mitigation. It has an exponential time overhead on top of that. Then you have post-processing over there. And then you have the computing that's preparing beyond that. All this code here is preparing classically. And the question is, how many times do you do that? So if you want to compute the time scale of your variational algorithm, it's a multiplication of that factor times that factor times that factor times that factor times that factor. In the end, I'll give you an example. If you want to do a simulation of a benzene 12 atoms molecule, you will have 72 qubits and you will have 300,000 polystrings times 1 million execution over there, times all the stuff over there. And in the end, you've got tens of years of computing with a computer that doesn't exist yet. Because you don't have the qubits today. Because 72 qubits with the quality able to execute a deep algorithm that doesn't exist yet. So let's look at I will skip stuff because I'm late. I'm skipping some stuff for you. I will show you some of the challenges we have to cope with to build those systems. We have a lot of engineering challenges. That's what makes it interesting. One challenge is to improve the qubit fidelities. You will see the big challenge there. The second is how do you manage error correction if you want to do large-scale quantum computing. Then you have to look at the cabling and electronics. Sizing that, like Neil said before, is a huge challenge. Then you have the energetics. That's why I'm doing the quantum energy initiative. How do you manage that system is not consuming the power of nuclear plants? It's easier said than done. That's a lot of work there. Then there are also some issues like how to connect the computers one with each other. How do you manage memory? How do you manage data loading? These are big problems. These are big problems consuming the bandwidth of many researchers, many companies, many labs in the world. So let's look at qubit fidelities. Currently, the qubit fidelities, you can lay out it simply. You take 2 qubit fidelities, that's the most harder one to get. You plug this in error rate. So 100% error rate is not good. You understand that? But what we need is to have less than 1.1 error rate to do something useful. And then you've got the number of qubits you don't take. So up to 127, that's the latest system from IBM. So, well, you've got many companies over there. All the companies that are below at the right of the 1% rate, I would say they are not in good shape. I would say they may die. Maybe not Google, but Rigetti or QC, I'm not sure about that future. IBM is making some progress, so increasing the number of qubits around the 1% rate. And you've got the track times for qubits. They are capped at 20, 30 qubits. It's very hard to scale the number of qubits over there. And if you look at what you can do with the system, if you look at everything that's below 20 qubits can be emulated on the classical system. Below 20 qubits, you can emulate that on your laptop faster than the quantum computer. So all the guys who are below 20 here, they just use their system just for testing. Then if you're in the red, below 0.5 over there, you've got too many qubits and too low a fidelity to do something useful. So forget it. Then you have the useful zone, the green one. It's interesting because you've got nobody there right now. Nobody is over there. You need to be there to do something useful in this area. So what you have to try to guess is who's going to get there. Is it going to be IBM, Google, Alibaba, others? There are some paths to get there. Maybe IBM can get there in about 1 year. Maybe it can be longer. We don't know. But you have to get there to do something useful. It's valid. But still shows the progress. Now, if you want to do a logical qubit, so you have to assemble thousands of physical qubits to create a logical qubit. It looks like this. So that's the so-called surface node. So you've got many qubits assembled in a circuit just to make one functional qubit with a perceived error rate that's acceptable. And I can use the same plot as before. So we take those guys who are over there today. The right one is unusable. You want to be there to do NIST first and then large-scale systems. So you need to build systems with millions of qubits. Maybe if you use so-called cat qubits from Alice and Bob, it's going to be easier because you're going to maybe fewer physical qubits than logical qubits. You still need to be there. So for instance, if you want to break an RSA key, you want to break the internet because it's your game, or you want to do some useful chemical simulation or financial portfolio optimization, you need to have at least 2,000 to 10,000 logical qubits, and you need to have at least 6 orders of magnitude more qubits in number than the ones you have today, and they have to be 100 times better than the ones you have today. You see the challenge. So, but it's like the guys who want to do nuclear fusion. It's like the guys who wanted to do the LIGO experiment about 30 years ago. It's like the guys who designed the James Webb telescope. It doesn't mean it's impossible. It's just a huge technology challenge. And there's another one, which is electronics. So let's take IBM or Google. This is the electronics just for one qubit. This is the cables and electronics just for one qubit in a superconducting system. Complex up to about 8 to 10 qubits with the green lines over there for without. But all the things in blue here are challenges. Technology challenges for the guys doing multiplexing, cooling, electronics. Just for amplifying the qubits that you read out, you need those 4 boxes for each block of 10 qubits. You need to miniaturize that because if you have 1 million of these, you will have a space problem. So you have to do some electronics engineering, sometimes involving quantum physics, but you have to improve the electronics to miniaturize those systems because you need to assemble millions of physical qubits to make it work. So that's a huge challenge. That's IBM, they do flexible cables. So that's the Quantum Energy Initiative that I've been co-launching with Alexei Oflev, Danny Spetsaucer, and Robert Putney. It's kind of worldwide initiative where we want to make sure that people work together to look at the energetics of the system. And the interesting part of that kind of research is that when you look at the energetic standpoint, you are obliged to be transversal. You are obliged to look at all the trade-offs between all these systems, electronics, qubit quality, algorithms, and you need to have a kind of full stack analysis of the system, and it can help you optimize the system because it's got a holistic approach. And it's a new way to look at this. And we have to push people to work together from research and industry in the industry space. And it starts to team up. We've got about 28 partners, 24 years old. We've got nearly 300 people in that community. Some people in the room are already engaged in that initiative. So, large companies like EDF, we're thinking about this approach to optimize the systems. I think I will stop there. And I have some freebies for you. If you don't know them, it's the file book. It's free, open source. Yeah, you can buy it on Amazon if you want paper, but you can download the book. And you can also listen to the podcast I'm running in French with Fanny Bouton. Half of the podcasts are news, and the other half is a discussion with specialists. And we're going to do the first one in English to be soon published with Simone Severini, who is the head of Quantum at Amazon. So we can switch to English slowly. Thank you. Yes, well, I've got some students ready for me for. Yes.
Thank you very much. Very interesting speech. You talked about the two supremacy.
Yes.
Google one and the Chinese one. For the Google one, the classic can hit the record. Yes. Now, classic we can do as function. For the second supremacy, what is the start of the R?
Well,
even this case,
yeah, I know.
Useless.
Yeah, the Google supremacy was initially compared to the IBM Summit. It was supposed to run 10,000 years on IBM Summit. Then IBM produced kind of new version using more memory that was supposed to last only 2.5 days. And then Xavier Vintal, Thomas Herral, one from CEA, the other one from Atos, and my student Meyer from the Flatiron Institute, they designed a kind of a tensor network-based algorithm that could help simplify the emulation of the system on a classical system. And I know that it runs on a HQML machine from Atos, but it's still fast, it's still slower. I think it's a couple of hours of computing with 1 terabyte of memory. It's still a bit slower, but it's not the same scale of difference that they had initially. But I would say that those supremacy experiments are not fair comparisons, because you are comparing a physical system with a classical computing system. You see, this pattern of water has billions of water molecules. Simulating that in a computer is probably a bit complicated, particularly if I throw the bottle over there. And but you want to put data there. You want to put data and data in, data out. LSP is using another kind of thought experiment. You say you shake a laser, you take a bottle of milk, the laser gets through the bubble, and then the light gets scattered through the bubble. Simulating that, emulating that on a classical system is very complicated, but it's got no use case. The boson sampling experiment in China and the other one made by Xanadu. Initially, it was not programmable, but recently, both in China and this year and in with Xanadu last year in June, they published a paper saying that they could program the system with some input data as the phase of the photon entering the interferometer, and they could do some computation. But what they have not proven is that you have a real exponential acceleration in those systems. Because you got a lot of overhead in the system. There still is some progress. It's still some progress. I'm still there until tomorrow evening, so you can fill me with whatever question you have. And I have to go to a call. Thank you very much.
Hello.